Hi, team. What's up, Eve? I saw your email.
Actually, we can talk about it after class. I don't want to take away from class time, and I think it might take longer than 5 minutes.
Copy. Let's see, substitution. Let's see here. Connor, I got your email. I'll look into that.
All right. Yeah, just let me know.
I look for people's names on what gets turned in, and I give credit for everybody's name that was on it, but I don't see a name. I didn't know what rooms I put you guys in. I just kind of made it randomly, so I have no idea who was where.
No problem.
So we'll get that sorted out. Okay. Do. Share screen. So test, I do want to say a couple things about it, just collectively. My sense of who's in this class and so forth is lots of you are, I don't want to say overachievers, but like you have worked your butt off, you're smart, you have really high standards. This is pretty hard material, and I'm sure some of you, I'm just guessing, but I'm sure some of you are like, man, that's a bad grade for me, you know. I totally understand that. I'd love to talk with you about that a little bit one-on-one. The average on this test was, I think, 79%, just FYI. Not going to go over the whole thing, but I do want to do a couple of them that are just kind of troubling. And let's see. A lot of people wanted to do arc length on this question, but there's a couple of 2 or 3 review questions at the start of the review that got at this. But the very fact that this over here is speed in miles per hour, and that this down here is hours, means that area, multiplying those 2 things together, would be miles. So the area under this curve is miles. It's not a arc length problem. It's an area under the curve problem. And it's kind of one of the classic examples in the sense that you work from a rate. When you take an integral, you're actually working from a rate back to the amount. Remember in Calc 1, we had an amount and we took the derivative and it got us the rate. Well, now in the integrals, we're going back in this direction. So I definitely want you to walk away understanding that, but that was a hard one because if you did arc length on this, then it's like, oh man, it's worth 10 points. Got to give you some, but
So the unit just would have been miles on that, right?
Yep. I noticed the problem is asking for find the distance the plane covers during this time. And again, that's a pretty cool question because you can imagine a plane actually doing this. In other words, its speed would be decreasing continuously. So it would be an E equation. So its speed is changing all the time. So it's slowing in its speed. And so, in a sense, without calculus, you would never be able to come up with a distance. So there's kind of a classic equation, distance equals rate times time. But all those problems before calculus, the rate was constant. Well, if a plane is, landing, like its rate is not constant, then they start landing, 50 miles away. So this is not uncommon. So it's actually cool that you can recalibrate that and actually figure out how far you traveled. I mean, again, we have GPS, so it's not like this is a real application. We have GPS, so you know how far you travel. You don't need any of this. But this was the impetus behind calculus, because remember, in history, people did not have GPS until a few years ago. But I would like to, and I tried to do this on the test as much as I could, but I was grading tests. Like when I left class yesterday, I graded till 8 o'clock at night. I mean, it takes forever to grade these things, but that's because I feel like I owe you a really good shake. I really need to look it over careful and find mistakes. And so again, I would invite you, as I always do, to push back, or maybe I missed something. Sometimes it's kind of hard to see, but I really take a lot of time with these. But I do want to do this question because I think a lot of people screwed this up, and to some extent that's on you. If you did not delve into the project deeply, then this would be hard. But if you did do the project, this is actually pretty easy because the shape isn't curved, and so it's a little bit of an easier equation. But what I'm most interested in actually is just that you can conceptualize these things. And I think maybe after banging your head against it on a test, I would like this to have happened on the review so that you aced it on the test. But at least with respect to going forward and not being screwed up on things. And because this is one of the coolest takeaways, and you can imagine, a part like that. I mean, you see things like this occasionally that people make or whatever. And the fact that calculus has something to say about it. So let's just take a look at this, the volume of this thing. Well, you got really a couple of choices. One would be shells, where if I said, okay, I'm going to take this slice right here, and I'm going to send it around that, I guess I'll call this the y-axis. I'm going to send it around the y-axis. Then this distance right here is clearly an x coordinate. Tons of people kind of got that all screwed up or got mixed up. And again, I'm saying this because that doesn't surprise me. As I said, many of you are really good students and you really work hard at things, but it's like, this is pretty hard material. Getting this in one pass is amazing. I mean, if you got an A on this test, you're really sharp. You're certainly sharper than me. This is tough stuff. So that distance is x. So in shells, you say 2 times pi times the radius times this height right here. Well, that height is, well, a y. So that's the basis of what shells would look like. And then the thickness of this is a little bit of x because it's horizontal. So that means I'm working in x's. So I'm very happy to see this x, but I'm not happy to see that y value right there. And I did tell you here, hint, you will need to generate an equation for the slanted line. A way too large number of you struggled to find the equation of that line. That is not good. But that's kind of what happens in a practical context like this, because you got to kind of come up with stuff yourself. So let's see, if I'm doing this because most of you did this. If you choose this to be the XY axis, then this would be the point, well, over 2 over 3, this is the 0.50. And then this is over 2 over 1 more. So this is over 3. And it's apparently up 4. So this is the 0.34. So if you use the 0.34 and the 0.50, you end up with a slope of -2. And then if you plug in the 0.50 or the 0.34, you end up with a plus 10, because that line is clearly going to hit way up here somewhere. So the fact that it hit up there at plus 10 kind of makes sense. So sweet. All I got to do is replace this y with 2x plus 10. And I now am working in x's. And then I look to see, well, what are the x's? Well, notice this kind of regime only exists between here and here. Like I can't let that keep going to the left any further. Otherwise, this isn't chopped off on the top right there. So this only goes from 5 to 3. And that's all you're going to get out of shells. Then you have to come back and sort of consider that inner shape, which you can do entirely just based on geometry. In other words, that inner shape is just an outer cylinder minus an inner cylinder. So if you used shells, that would be your approach. And again, I just want to highlight, like this, I make this look easy now, but I've taught this a lot of times. Like this was not this easy to me when I first took calculus either. It takes time to conceptualize this. The other option would be to do this with washers. So in the case of washers, it would be, I'm taking this slice right here. My slice is horizontal, and I'm sending that all the way around both sides. This is always so hard for me to draw. Something like that. So I've got this outer radius, which again is x. So that's like the x of the line. And then I've got this inner radius, which is actually constant. It's just 2. So pi times radius squared times height. That's the volume of a cylinder, except for in my case, the radius is the x of the line. And my height is a little bit of y. That's not so good. Again, we see that happen every time. We end up with x's and y's. Minus the inner cylinder, which would be pi times its radius squared. Now, there's a couple of ways to do this. You could include this in the integral and say pi times radius squared times a little bit of height. Or you could just save this whole thing for later. Like you could just save that for later and come back and subtract out this whole, to subtract it out as a cylinder. Like do that as a regular algebra problem. Most of you included it, which is fine. So awesome. Well, I'm stuck working with y's. Okay, well, this 2 over here doesn't care that it's working with y's, but this x does. So then I got to resolve that equation up there for x. So if I subtract 10 from both sides and then I divide by -2, there's what x is equal to. So I'm going to have to throw it in there and square it. And now that I'm working with y's, I look up here and I say, okay, well, where does that thing exist? Well, it exists from y's of 4 to 0, since this is a height of 4, and there's no reason it can't go all the way to the top. So that slice up here would be fine. There it is. And the slice down here is fine. There it is. So that slice is just going to slide up and down. Now, again, and some of you did not take advantage of this in terms of time, but in many places, I mean, 3/4 of the questions, I said use the calc button, because the point is, these are hard just to set the dumb things up. So the point was not take the integral. The point was, with a few exceptions, just set the stupid thing up and then be done. A lot of you started doing a little bit, but I mean, what I'm saying on this question is the best thing you could have done here is just write out 4 to 0. Maybe you pull the pi out front and you have y minus 10 over 2, which you don't even bother to simplify. That is squared. It's minus 2 squared dy. Done. Throw that thing in my calculator, or Desmos. Desmos is a little easier to type that kind of thing in. Done. Enough people screwed this question up. That's why I'm kind of doing it for everybody. But again, I would like to meet with you one-on-one and talk about whatever went wrong on yours if my notes weren't clear enough. And so what about surface area? Let's quickly do that. And I said only the slanted portion of this thing. So what you're doing is taking a stripe of this and sending it all the way around the shape, like so. That's an arc length, and I need the circumference. And so again, this is the x coordinate of the line. So it's 2 times pi times the radius. That's the circumference. Now times that arc length, which is 1 plus either y prime squared dx or 2 pi x 1 plus x prime squared dy. It's up to you. It doesn't make any difference. So this one is way easier because this is x, this is already x, and y prime is dy dx. So I have the equation up there. Dy dx is just -2. So if I throw a -2 in there, and then I realize, hey, I'm working with x's. Well, what x's does this exist for? What x's does this exist for? Well, it's from here to here. So just like the previous problem, that's only from x's of 5 to x's of 3, because the thing's got to slide from here to here, and it doesn't get over into here at all, because it's just that outer shape. I didn't have to, in this case, say use the calc button, just because this is just a constant. This is 1 plus 4, this is 5, that's the square root of 5. And so this is actually not hard to take actually by hand. What if you did the other one? Well, then you say, okay, great, I'm working with y's. X is equal to, we said y minus 10 over 2, so that'd be 1/2 y minus 5. I'm writing it that way because then x prime would be positive 1/2. So okay, 1/2 goes in there. And I'm working with y's, and so this can't be x, this has got to be y, so I'm going to have to replace that with 1/2 y minus 5. And then I'm working with, well, now y values. And so what y values does this exist for? Well, because that's 4, then it goes all the way up from 4 all the way down to 0. So either one of those two would produce the answer. But again, it's a lot to ask. You're mixing up, volumes, and sometimes you're doing surface areas and, all different shapes. And I mean, to not flub up something on this test is, even if you find yourself looking at your test going, why did I think that? That was dumb. I knew that. I mean, you're going to do that some. So for those of you that are, overachievers and, it's like your test grade is 15, 20% lower than you're sort of used to getting, like, cut yourself a little slack. Like, man, many of you guys are just working hard. You care, you put all this time into stuff. Like, chill pill. This is challenging to get in one pass. But I do think it kind of helps. That's why I said I'd love to go through every question with you that you missed, just to kind of help you walk away going, oh yeah, okay, I see that now. Any other broad comments that you want to make, or questions that you want to ask that might belong in the larger group of us, not just between you and I? I have a note on this test from the last time I gave it last year. Your average was, as a class, was 10% higher than last year's class that took this. So as an average, which of course you don't care about an average, you care what you got. But as I said, you guys are really sharp bunch, and a lot of you really care and have really good math minds. And I know I'm saying that kind of generically, but wow, I mean, you guys are sharp folks. So as I was telling somebody yesterday, I think it was a different class, but how many things in life can you see once and then you got it? lots of things don't fall into that category. And this is certainly one of them. Most things in life, you have to see somebody do it once, then you try it yourself and realize, oh man, I didn't pay that close of attention. This is hard. And then you maybe get some more instruction from that person, and eventually with a bunch of practice, and you can always practice more. I mean, all of you could practice more. Who can't practice more? But you got to balance that with your other life. And, most of you seem like you're putting plenty of time into this. My guess would be that for many of you, this is the worst math grade you ever got, because some of you didn't, some of you made more mistakes. But anyway, I have, so I linked your test back with some comments that I wrote on it, and I have your test saved here. So if you want to meet sometime outside of class or after class and pull your test up and just look at a couple of things together, I usually take time to rename them, because some of you put your name on there. Some of you save it with your name in it, and some of you don't. This time I was kind of lazy and didn't write your name over the top of it, so it might be kind of hard to find yours this time. But anywho, okay. Huh. So let's see, let me take stock here for a second. Where the heck are we in this class? We are in our final chapter, chapter 8. And you may have noticed we skipped chapter 7, which actually coincidentally we're going to do some of in Math 253 if you stay the course in this. And I'll talk about what Math 253 is before the end of this class. Actually, I should maybe say something about it right now, just because you're kind of signing up for classes. But again, feel free to ask me one-on-one questions about this. But Calc 3 is a class that, so we have Calc 1, 2, 3, 4, and summer is Calc 4. When I was in college, effectively Calc was a 3-term sequence, and it was effectively Calc 1, 2, and 4. So Calc 3 never took it. It's really cool, but it's an unusual class. So it's, if you had to skip one, it's the one to skip in a practical sense. Calc 4 is a lot more practical for a lot of degrees, but Calc 4 is really a challenging course. It's a big step up from what we're doing in here. But just to preempt something, what Calc 3 talks about primarily is infinite series. For instance, if you added up 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared, but you never quit, do you think the answer to that is a number, or is it infinity? You never quit.
It's 1.
You have infinitely many, infinitely small things. Does it make sense by the time you get out there ways? Like even right here, you're already down to 1/16.
So is it 0?
No, because like this is already 1 right there, so it can't be 1. This is a 4th, right?
I know.
How is it not
1
infinity?
half plus 1/4 approaches 2. This one is a different series, though. I'm going to guess 1.75.
I was going to say almost 2.
Yeah, isn't this interesting? It's really an interesting question. Now, by itself, that just looks like nerds at play, like people just asking interesting questions. But it actually turns out that you have all these buttons on your calculator that you utterly take for granted. Like if I say, hey, okay, get your calculator out and take the sine of 1.2 radians or something, and you just kind of expect your calculator to spit that answer out, as you might well, since it costs $100. But the reason it exists is because of these type of infinite series. It turns out that you can actually rewrite sine as a polynomial equation. And I did show you a little of this back when we were looking at the derivative of sine last term. I showed you how there's an infinite series for sine. In other words, it looks kind of like this expression that I just wrote out. And you can actually replace all the weird functions like square root, like e to the x. You can replace all of them. Tangent with statements that look like this, but very importantly, dot, dot, dot. They literally never end. And so these infinite series are the reason you have a calculator. It's not technology. It's somebody found a formula that they were able to put in there.
Well, yeah, that makes sense because computers can really only like add and subtract on the very base level, and then everything else they're doing is just more complicated versions of that. Just somebody figured out how to program it into the computer to make it do.
Yeah. So 253 is really a neat class. I mean, if you have the time, even if you don't need it, but you have the time and you like math, it's something that was a big hole in my math understanding until I taught it to myself last year, and I taught it last year for the first time. But oddly, I'd never taken it, and it filled a hole in my mind about kind of how the world works a little bit. So it's really cool. However, there's not a lot of degrees that need it. So the only thing I would say is, look into it based on time and money. Look into where you think you're going right now, and then kind of make sure that you need it. You could skip this and then take 254 in the summer. That's not ideal to have a summer class, but again, 254 is also really hard. But basically in 254, we're going to do calculus in 3 dimensions, like this weird looking lampshade I have right here. I mean, see that kind of cool 3-dimensional curve. So we're going to talk about like a plane that's tangent to that curve. You can imagine if I pick a spot on the corner and I lay paper against it or something, there's a tangent plane to a 3-dimensional curve. And so there's no new math in Calc 4, but we're going to jump an entire dimension. And that also filled a huge hole in my understanding teaching that class last year. So anyway, just a little bit of a kind of a forecast in terms of registration. Also, one other thing I'll say quickly is Math 261 is offered in the spring, which is linear algebra, which is we've been using a matrix a little bit to solve some of our 3 equations, 3 unknowns problems. And it's really a course that's designed around how does that work? How do you solve 3 equations, 3 unknowns, 4 equations, 4 unknowns, and what's kind of the theory behind it? And of course, mathematicians have taken it really far, and so you end up learning about vector spaces and all these crazy matrix functions and so forth in that course. But if you haven't done this before, I mean, a lot of people sort of need Calc 1 and Calc 2, but then it becomes kind of nebulous. Like start looking into wherever the colleges you're going after this one, and make sure you scope out what's the degree path to what you think you're doing right now. If you're in between 2 courses, if you're ever going to need these classes, you should take them now while this stuff is fresh in your mind. You've noticed that like derivatives have been a part of this class. We've needed to take derivatives to do things like for arc length, and all of a sudden it dredges up what you had from last term. Well, imagine sitting out an entire year and then taking that, it's like, oh, that's not good. So if you ever are going to need 253 and 254, you want to, even if your attitude is like, knock them out, get them out of the way. They're a prerequisite that I need to get rid of. I hate math, but I just need to get it over with. Well, it's, way easier to get it over with while some of this other stuff is fresh in your mind. Any questions about that? That was kind of vague and quick, but.
But you made me reconsider what I was actually going to be doing next term, because I didn't think about the fact that, oh yeah, Calc 4 won't be just offered after Calc 2. It's going to be offered in the summer.
Yeah, it's kind of a bummer. We've talked about, because way more people need Calc 4 than Calc 3. We've talked about kind of switching the order, but then nobody would ever take 253, and it is kind of a neat class, and so it's kind of a tough one.
Yeah, I'm wondering, like, I would definitely need that for a math minor, right?
Yeah, and that's in my case. That's what happened to me. I was in college and I liked math, and I had calculus in high school, and so I just kept taking a couple math classes, and I ended up getting a psych degree, which is a waste of time. But I pretty much had I was like 1 class away from a math minor, so I thought I might as well take that, because at least it goes on your academic record, like you actually accomplished something. You have a minor as opposed to just took some math classes. So I ended up with a math minor, and then later on decided I think I want to teach math. So then I went back and finished a math degree. But my math degree was kind of teacher focused, so it was more how to teach math as opposed to being just awesome at math and taking all the math courses. So that's why there's kind of holes in my what I know.
Yeah, I just know that I know that like with the embedded systems degree, like it's basically 2 or 3 classes shy of a math minor, you know? And so I was considering doing that as well, you know, with it, but it's like, I'm trying to figure out what I should do while I'm here at RCC, but
Yeah, both. And my experience too was the teaching that you get at RCC is a lot stronger than at universities. In my opinion, based on my experience and what I've seen of other teachers, mainly because community college teachers are more teachers, but at universities, they're doctorates who are studying math, and then they descend from their holy mountain to come down and teach some boring little subject like integrals. And I found it very hard to learn in that environment. I'm a slow learner. Like I know it looks like I know this stuff pretty well, but it's because I've taught it a number of times now and I really get it, but I did not get this easily on the first pass. I had to work at it. So, you know, and you just have a lot of holes in your knowledge. I mean, I just remember asking questions of them. It's like, oh, that's an algebra problem. You should already know that, which is kind of true. They're not wrong. However, you know, I don't. So it's a lot more compassionate here, I think, in the approach that you get. So whatever you can take at RCC, both because it's cheap and as a general rule of thumb, you get more caring instructors that are more teachers than smart people. Because if somebody's teaching a class like this needs to be easy to them, like no prep, no problem, totally easy. So it's not about the material, it's about how do you communicate the material. So I'd take what you can here.
okay, thank you for the advice.
Yeah, so anyway, happy to talk with you more about this given your own situation at a later point. So what we're doing in chapter 8 is really returning to taking integrals again. And I've been hinting at this. So, and I like the way this book is organized in the sense that we just took a whole chapter applying integrals. We didn't know a lot of tricks. We knew substitution and we knew the power rule basically. And the focus was on cool things that you can do with it, like finding volumes and areas and surface areas and arc lengths and all these, you know, genuine applications of calculus, which is why it was invented in the first place. Now we're going to return to what mathematicians do, which is let's just take the integral of everything. We got things we can't take the integral of right now because we're not as good at substitution as we need to be. And so that's what chapter 8 is about. Back to just taking integrals of ridiculous statements. And so the more challenging aspect of that will start kind of, well, tomorrow, where I teach you a second technique that is sitting in your note sheet, I think, called integration by parts. But today what we're going to do is re-look at substitution, but just take a little bit deeper and then also kind of refresh your mind. So 8.1 is really just substitution. So let's kind of, I don't know, get this back and then tackle some slightly harder problems. And so let's take a look at this example. What would you do with this? And for the most part in this section, you're going to get what mathematicians call, as I've told you before, indefinite integrals. In other words, the point is not to get the answer to this to be 16.2. It's just, can you take the integral of the dumb thing? So you very seldom will actually be getting numerical answers. It'll just be take the integral of that thing. So I just want to show you a couple of cool things. Now you already have a sense of how to do this question from before, but again, it's been, you know, a month. And so we never like, one option for this would be to let U, or whatever letter you're picking, be the, what am I doing? Be the denominator, because we don't like the fact that there's 2 terms down there. If this 6 wasn't there, then we would have just divided both of them individually because of distributive law by X, and then we could have just used power rule and it would have been very simple. But that X totally screws things up, and so, well, get rid of it then. That's our classic, one of our classic substitutions. And so then you say, okay, cool, that's really great, because then du equals dx. So I can just switch du from dx, and then I get to rewrite this thing. So my interval becomes u on the bottom, du out here, but then I've got that x. Notice that 2x on top, that x doesn't cancel, but this is solvable for x. In other words, I can add 6 to both sides, and so x is that, so then I can just replace x with u plus 6. And so that's much nicer now. So you say, okay, that's easy. That's 2u plus 12 plus 4. So that's 2u plus 12 plus 4 is plus 16 over the top of u. And now you actually are free to divide them both by u. So you can split them apart now. Think of it as like undoing addition of fractions. And so we said that integrals love plus signs. And so u divided by u is gone. 16 divided by u is not gone. And now I can treat those two separately. And so you would say, great, the 2 grows a u, if you will. And then what do you do with 16 over u? That was one of the tricky ones. Remember, that's 16u to the negative 1. And if you try to add 1 to that exponent, you get 0. So the power rule isn't working, which should kind of prick your mind. Oh, that's right, this was that weird one. What's the answer to the integral of 1 over u?
The natural log.
Yeah, natural log. So that's the one exception sort of to the power rule. And then you just go back and stick your x minus 6 back in there. So it's 2 times x minus 6, and it's 16 times the natural log of x minus 6. And if somebody's annoying, they make you throw a plus c in there, and like, bam, there's my integral. I found it. And so you knew that from before, but that's probably good to kind of, get your mind circulating back again. And if I'm alone, as I often say, I'm not very sure I got this question right, because I mean, I know I understand the concept, but I could have lost a negative sign or done any kind of dumb thing. Remember, it's always okay to go back, and you want to look at a graph to do this, but go back and say, I think I'll just evaluate that from 7 to 2. And then I'll evaluate this from 7 to 2 and make sure they're the same answer, because then that would kind of check to make sure I got the right answer. But remember, you got to graph this, because there could be a hole in that graph. And there is in this case. Does anybody see it? My choice of 7 to 2 is not good. Can anybody see that?
Was it because of the 6?
Yeah. What's this graph going to look like because of that? Because there's an x minus 6, that means x can't be 6, right? That creates that asymptote sort of thing. And so I just chose a range from 7 to 2 that included 6. And so not good choice. That's what I'm saying. You got to graph this stuff. So this graph is divided at a vertical line of 6, and there's like one graph on the right of 6 and one on the left of 6. And so if I went back and said, armed with that knowledge and said, oh, that was dumb, I'm going to go from, like 9 to 7, like that would be better. Do you see what I'm saying? So, I'm not checking this probably if it's not a test. But, there's a lot of stuff I can do wrong. So should think about that. But let me show you kind of another approach to this. This isn't any better, but let me just show you another option, because really what you want to do is get creative. You actually can divide this. In other words, if it says 2x plus 4 divided by x minus 6, can't you do long division on this? That's what that means, right? In other words, just before you take the integral of it, do something to it. So let's see, x times 2 would be 2x. And if I multiply that out, I'd get 2x. And then 2 times 6 is minus 12. I'd subtract those. 2x minus 2x would be gone. 4 minus a negative 12 would be 16. So that means this statement right here, 2x plus 4 over x minus 6, is actually the same as 2 plus the remainder 16.
Wait, isn't it not 16? Because you have a positive 4 and a negative 12?
No, because I'm subtracting all of this. I'm subtracting.
Oh, yeah. Okay. Never mind.
Thank you. Good question. So maybe that's easier to integrate. it really isn't in this case because you're still going to have to go let u be equal to x minus 6. So you still have to make that substitution, but we love this plus sign. Does that make sense? I'm really happy with that because the integral of 2 is 2x. Like I could just kind of say, sweet, that part's done. So let's just at least see we get the same answer. So this is the integral of 2, and I'm going to write them separately. Integral of 16 over x minus 6. So I'm already done with that one. 2x, awesome, sweet. Here I'm going to have to do the same thing as before and let u be equal to x minus 6. So this integral would become 16 over u du. Notice that did save me a little trouble because I didn't have to replace the x on the top. There's no x on the top anymore. And the integral of 16 over u, as we said before, is 16 natural log of u. And then I would getting all done then, putting this all back together, I'd say 2x plus 16 natural log of u, but u was x minus 6. What's wrong with that? I didn't get the same answer. Did I? I got part of it, but I didn't get all of it. What happened? Do you agree this one is actually 2x minus 12? So I got the 2x and I got the 16, but it's like, where's the minus 12? I didn't do anything wrong. It's the fact that there's plus a constant on the end of this. So that constant accounts for the 12, if you will.
So wouldn't that mean that that top thing wouldn't actually need the plus C on the end of it because it already has a C in there?
No, because that plus C could be plus 912. And if you take the derivative of that statement, the derivative of 912 is 0. So you can add any constant on to the end of this. The fact that there just happens to be a 12 there, but that doesn't have to be a 12. It could be any other number. So I still need that C up top, actually.
Okay.
But remember, when you're taking a derivative, constants go away anyway. So if I multiplied this out, when I took the derivative of that 12 up there, it'd be 0 anyway. And so I'd still get back my original problem. And so that's kind of demonstrating what C can do or what it can be.
That was kind of my first thought, was that when you took the derivative, it would just go away.
So if I evaluated this one at 9 and 7 again, that 12 would make no difference whether it's there or not, because 12 would be in the first answer. When I stuck 9 in, there'd be a 12. And then when I stuck 7 in, there'd also be a 12, and 12 minus 12 would be gone. And so constants make no difference. So that's why it's kind of like plus C. So it could be anything if you have some reason for it to be something. And again, there's some cool applications for that, why that C matters coming down the road. So that's just an option, like just something to think about. So let's take a look at all I really want to do is just kind of blow through a whole bunch of examples here and get your brain thinking. And I do need to pick up the pace. This one is really not good. This is genuinely new. The last problem was not new. But this one you got to think about a little bit more. Now you need to be looking at your Calc 1 sheet right now. Your Calc 1 note sheet.
Could we use trig substitution for this one? With
Yeah.
the x squared plus 4 on the bottom? Because that looks familiar. I think that's tangent or something.
That's
I
right.
want to say.
Yep. And that's where we're going to go in some coming chapters, is to teach you there's some really creative substitutions. Notice x squared plus 4 looks a little bit like the Pythagorean theorem in right triangles. And since right triangles have trig involved with them, there's some really surprising substitutions. But we don't have time to do this, but But if I said, as we did last time, I'll let u be equal to x squared plus 4, that just doesn't work here. And I would encourage you to go like try that. I wish we had time to soak on this a little bit longer. But that isn't going to help in this case. And you might even think, hey, that would help because isn't the derivative of x squared x? And so wouldn't this cancel up here? And it won't. And frankly, it's because of that 2. If that 2 wasn't there, then we could have done this as substitution. That substitution would have worked, but that plus 2 is kind of screwing that up. So play around with that a little bit and see what I mean. But I guess I'm going to have to.
Yeah, so I checked the note sheet and it said arctangent is equal to x squared plus 1. So wouldn't it just be 4 times arctangent of x? Is that right?
Yeah, that's exactly where this is going. So a number of these questions, I'm gonna load this up real quick so you can see it. So there's some things that are built in that you can steal from before, but we want to be able to make these for ourselves. So we're going to talk about trig substitution a little bit later on. But if you see stuff on the bottom that looks like the Pythagorean theorem, you kind of want to note that because that's going to allow you to get out of this mess. In other words, this one right here, would you agree, to Eve's point, this looks an awful lot like that one? Now notice this has to be a 1 and this has to be a 1. But
hey, Doug.
Yeah, go ahead.
I'm not sure if it's just me, but I'm seeing kind of a big gray striped box.
Thank you.
Okay. Yeah.
Now you're seeing it. Apologize. Let me go back so you can. So here's the note sheet from Calc 1. And you probably could not make this for yourself anymore, but at the time we made it. But the derivative, remember when you go this direction, you're taking a derivative, because there we are up there taking a derivative. The derivative of inverse tangent was 1 over 1 minus x squared. Well, hey, if that's true, then doesn't that mean this would be the integral? If I had the integral of 1 over 1 plus x squared, that'd be equal to the arctangent or inverse tangent. Well, doesn't our problem look kind of like that? So the question is, can we get it to look, well, a lot like that? That's the question. So unfortunately, I don't have 1s in these 2 positions. And I even have an x up there. And so it's kind of like, well, it kind of looks like that, but not really. So let's see if we can use that to get ourselves out of this mess. Note. I feel like I need to change colors. Note. The inverse tangent of x, the derivative of it is 1 over 1 plus x squared. And ours looks kind of like that. Well, not very much like that though. But would you agree that you could do this? Would you agree you could separate this into 2 problems? Again, think decomposition like we did just a minute ago. Think about that as a fraction problem where the fractions have been added. Would you agree this is equal to this plus this?
Yes, I would.
Yes. And this one over here can be solved with normal substitution, because if I let u be equal to x squared plus 4, and therefore the derivative of that is 2x, then that 2x, that x is going to cancel the x on the top. So again, we love to see an expression down here where its derivative is sitting on top, because that means it's going to cancel, right? So let's finish that. So that means this problem becomes, well, x over just u, but then I've got to replace dx, which is so important to write there, which I was lazy not to write. Dx is replaceable with du over 2x. Sweet, then those x's actually cancel. So then that problem just becomes, well, there's a 1/2 1 over u du. Hey, sweet, I can take that. That's natural log. So that's 1/2 natural log of u, and then I can put x squared plus 4 back in there. Awesome.
Could we start this one a different way? Like where we take 1 divided by 1 plus x squared and then multiply it by x plus 2 divided by 4?
Yeah, in other words, what you're saying is, could we try the division kind of approach to this? Is that what you're saying? Or are you talking about the next problem?
I don't think so. It's related to what Eve brought up, the arctangent, I guess.
Yeah, so you're looking at the second problem. Your comment is pertaining to the second question, right? So would you agree that doesn't look quite right? Like we got a 2 and a 4. That's not good. So remember, that's still just a fraction sitting there, and I can do math to it. So I really need this to be a 1, and I can't subtract 3 from it. But what can I do to fractions? Well, I can multiply the top and the bottom by the same thing. Let's see if that goes anywhere. If I multiply the top by a 4th and the bottom by a 4th. So now the top is 1/2 and the bottom is 1/4 x squared plus 1. Does that help?
I don't think so, because isn't your main problem the fact that you don't have an x on top
Well,
because of your x squared on the bottom?
I don't want an x on top because I'm trying to get this thing to look like this.
Oh.
Since the inverse tangent is 1 over 1 plus x squared, I'm wishing this was a 1 and a 1. If it was, I would have said the inverse tangent, oh good, I'm done. It's the integral of it is just inverse tangent. So I'm just trying to figure out, can I get it to look like I need it to look? And so notice by multiplying by a 4th, I fixed this and got this to be 1, but now this one's screwed up. Does that make sense? So the question is, can I get myself out of that mess? Is there any way to get it to look like it's supposed to look? Do I care that there's a 1/2 on top? What's your thoughts on that? Do I care there's a 1/2 on top?
No, because that just changes the variable at the end after you take the integral.
That's exactly right. In other words, I could pull the 1, I could pull that. Remember, all constants can be pulled out front. So I could pull that 1/2 out front. Now there's just a 1 up there. So it's just that.
Wasn't there a thing that you could time, like if you times 4 by the arctangent, would it equal like x squared plus 4 on the bottom?
If you multiply by the arctangent. I'm thinking about that. What this illustrates is that, really to take integrals takes a lot of creativity. You got to try stuff. I made this problem up randomly, which may mean it won't work. Like you actually can't accomplish it. Or maybe it's going to take some other substitution technique like Eve hinted at, some kind of a more sophisticated substitution. But I'm having trouble getting this to look exactly like that. So if I had made the problem up with this being a 1 right here, does it make sense it would have worked? But maybe with that being a 4, it doesn't work. Real integrals, and again, this is just the realm of mathematicians that just rather than going outside and playing, they're just going to sit down and write down some idiotic statement like this and say, can I take the integral? But is there some way that I can do that? Which is kind of cool and kind of crazy all at the same time. Would you agree with that? I hope you have enough creativity to you that you see stuff like this as kind of a challenge. So I'm looking at this right now thinking I'm not seeing a way out of this. I'm feeling, unless we do something different, I'm thinking that's causing us to be stuck. I got this 1 to appear, but then the 1/4 came with it. And so maybe I can't get this to look like inverse tangent.
I disagree.
So what's your idea?
I think that if you pull, okay, go back to your original equation. Can't you pull out the 2 right from there
From this
on top? No. Your separated equations.
Yeah.
Yeah, that one. Can't
Yep.
you pull out the 2?
Yep.
And then can't you apply some sort of U substitution?
Well, I'm not saying we can't do this. I'm just saying we can't get it to look like inverse tangent. And I'm not sure. I'm actually not sure that that's true. So just to point out what Eve is saying, if we're sitting here with 2, like, couldn't I have just pulled that 2 out front from the beginning? That's what Eve is saying. Yeah, absolutely.
When we set it up at the very top, I guess, instead of using those 2 integrals, the x divided by x squared plus 4, and then the 2 divided by x squared plus 4, could we use 1 plus 1x squared times x plus 2 divided by 4? So that way the 1 divided by 1x squared, the integral of that would just be arctangent, and then we could just, I think x plus 2 divided by 4 is an easy integral.
So if I'm tracking with what you're saying, you're thinking of this as like plus 1 plus 1. So you have sort of 3 integrals. Is that what you said, Martin?
Not really.
Try.
I think, let me just multiply it out. The original one is, what's the original?
X plus 2 over x squared plus 4.
I have one more thing I want to try.
Yeah.
So I think I got it unless I made a mistake. But if you take out, so if we start from our plus 2 over x squared plus 4 on that equation, if we take out the 2 and then we apply U substitution, so x equals 2u, don't you get the answer 2 times the integral of 1 over 2 times per, if you can write it down. I don't know if you're following what I'm saying.
I am. So let's try.
Okay.
Let's try Eve's idea. She has a pretty good idea here that might actually get us out of the woods. So are you agreeing with me that 4 is causing us problems? Are you feeling my pain? Because I'm trying to get you to understand the difficulty of the creativity that's involved in taking integrals. So Eve came up with what I consider to be a pretty brilliant idea. Let's watch this happen now. So if I replace that x now with 2u, and that would mean du equals dx divided by 2. Why am I writing it that way? There's no reason to write it that way.
Actually, I was more going towards the fact that you can pull the 2 out. So you have a parenthesis of u squared plus 2 plus 1 squared. Wait, hold on. Yeah, you're going the right direction. Never mind.
Yeah, I think I understand what you're saying. So then I'd replace dx with 2 du. Do you think this is going somewhere? Can you see where Eve's going with this? Well, doesn't this become 2? Let's see, there's 2 2's. I'll pull that n2, I'll pull it out front. So there's 4. And now I have 1 over 4u squared plus 4. That doesn't look like a 4. Is that good? That's extremely good because now it's 1/4 times u squared plus 1.
And you can plot the 1/4, right?
And that 1/4 comes out so that outside there's just a 1. And now you have 1/u squared plus 1. So that's the arctangent of u. I think Eve found us a way out of this mess with a very creative substitution. So let's see. So in total then, if I go back to the kind of the beginning, I would say 1/2 natural log of u. For that problem, u was x squared plus 4. So that's x squared plus 4. Now for our problem, all those 4's ended up canceling. And so we just have plus the arctangent of u. I should have used a different letter because notice down here we used u to be something else. So notice u is x over 2. So this would be the arctangent of x over 2. I think that's right. You see how tricky these are though? What you're doing with integrals long term is trying to get it to look like something that you're comfortable with. That's kind of what it comes down to. So, you know, one of the things we did with this problem is we said, well, I don't really like that there's a plus sign up here, but we can split it apart. Like that's just usually you're adding fractions and putting them together. We unadded them, we took them apart. And we like this. That's familiar to us. That's a question we had back in chapter 6 or 5 or whatever that was. And so it's like, okay, no problem there. And then the second one looked a little bit like inverse tangent, but we still had to be pretty darn creative to come up with a way to get it to look exactly right. I say we, meaning Eve. And so we found a way out of this mess. I mean, that's amazing that that's the case. And I don't know about you, but I still kind of find myself wanting to check this somehow. We don't have time, but I don't see a mistake in it. But I'd really like to, well, maybe take the derivative of that. I mean, that seems like a pain right now too. But I'd like to take the derivative of that statement and see if I get my original problem back, or as I said before, maybe I go graph this and find a couple of numbers that I can stick in here for the limits of integration and then go plug it into the one on the bottom and see if that actually worked. But integrals are both annoying because they take a lot of creativity, real integrals, random problems. But they're also kind of cool because they really represent challenges. Now, what I have to be careful to do as a teacher is give you problems that are within your ability to do, right? Like I can't just make something up totally randomly because it might not be possible, or it might take ridiculously complicated substitutions. And I'm going to show you some of those going down the road. Try this one. The integral of, I'm going to write it the way the book might write it, just so that you get used to seeing that. That's kind of an annoying way to write this. I'd rather see a 1 on top and the dx out at the end, but that's not wrong. Now this is not good. It would be great if on the top there happened to be a 2x plus 4 up here. Do you agree that'd make this problem really easy, because then the bottom, the derivative of the bottom equation is sitting on top, but there's not. There's nothing up there. There's a 1 up there. So, you know, what could I do to this? And we've had this happen. There on your test, you had expressions that had a parabola on the bottom. And that's something we've never been able to handle before. We've been able to handle it when there was just a linear, like x minus 6. We can handle it if there's a linear equation on the bottom. And then we just saw that you can handle it if there's a parabola on the bottom, but you can't have a middle term. Like if that had an x term in it, that'd be no good, right? Like we were able to get that to look like inverse tangent, and so we got out of this mess. But if that had had an x squared plus 7x plus 4, we would have died. And so can you see the progression? Is there any way out of this mess? Thanks to that stupid 4x? The answer is yeah, if you employ, again, another very creative idea here that, and the heartbeat of mathematics is not, me letting you think about this problem for 6 seconds and then doing it for you. Like that's the heartbeat of mathematics is turning you loose with this question. And, it takes a week for you to play around and try stuff. And maybe the end of the week is nothing worked. Maybe you did figure it out. So I don't like this. I don't like teaching this way where I show you a problem and I give you 6 seconds to think about it, which is not even close to enough time. And then, then I tell you the answer. But obviously we got to strike some kind of a balance. We're not rich enough just to sit around doing mathematics all day long. You have other classes and other lives. And so, what do you do? But can you still complete the square? In other words, if this had been x squared plus 4x plus 4, that would have been great because that factors to x plus 2 and x plus 2, which I can write as x plus 2 squared. That'd be really cool. Well, can we do that? Sure. I'm going to write the 1 up there. So that's true, except for I'd sort of have to rewrite that as 4 plus 9. And so this would actually be x plus 2 squared plus 9. Do you agree that cool little trick just made it look a little bit like the previous question? X plus 2 is now squared. In other words, it's kind of like not an x term. Could you just replace x plus 2 with u, and now you have u squared plus 9? And then doesn't this look really similar to what we just did a minute ago? So
I'm just blown away what you just did with the 4 plus 9 thing. I've never seen that before. And it makes sense, but I have never seen that before.
Yeah, completing the square is kind of an interesting trick, and that shows up occasionally throughout math classes, but usually it's not taught in a way that allows you to really reason it out for yourself. But this technique was the basis by which the quadratic formula was created, completing the square. So yeah, we can talk about that more after class if you want to. It's really cool. So based on what we just saw a minute ago, would you agree that it would be really cool, just to kind of kill 2 birds with 1 stone, if what's inside there was actually 3u? You understand why, from Eve's idea a minute ago, why I not only want that to be u, but I'd even like it to be 3u? Why do I want it to be a 3u?
Because if it was squared, it'd be 9u squared.
Yeah,
And then
this
you
would
could
be
simplify
9.
the 9s.
Yeah, and then those 9s could factor out, and then I'd have u squared plus 1 again, and it would look like inverse tangent. So notice your substitutions can be sort of messy. Is there any reason I can't just say let x plus 2 be equal to 3u? It's not like I have to say let u equal something. Just say I wish that x plus 2 was a 3u. Great.
For some reason, this feels like we're making up math instead of letting math guide us. Like for so long during math classes, you kind of let the math problem guide you.
That's
And in
very true.
circumstance, I definitely feel like we're controlling the problem.
Yeah, you're in dangerous ground here because you're making this up. Remember what you're really trying to do, as I said a long time ago when we were first looking at substitution, is you're staring an integral that is just too big and tough for you to beat. And so you try to switch it into something that you can beat. And this is going to work. But man, it takes a lot of creativity. This is a very hard thing to teach because, how do I give you a test on this? That just feels sort of not fair. Do you know what I mean? Like, how much do you have to practice before you'd be able to come up with this? I got to be careful to give you a lot of practice and give you questions that are kind of inside that realm. Because as I'm going to show you later, the creativity that is involved in some really open-ended kind of questions is incredible. Finding the integral of secant is an example. We're going to get to that later on, but Man, the substitution that you have to come up with is breathtakingly brilliant. I never would have thought of it. Well, let's keep going. So that means dx is equal to 3 du. And so, okay, what do I got here? Then I got 1 over 3u squared, which is actually 9u squared when I square it out. And then dx is replaceable with 3 du. And so this is awesome because then I can pull that 3 out front. And then I can pull this 9 out front. And that leaves that. Do you agree with that? And now this is recognizable as inverse tangent again. Whoa. So that means the answer to that is inverse tangent of u. And then there's a 3/9 out front or a 1/3 out front. Now, if I go back here, I think, okay, well, there was never any u's in it. Notice now I have to solve that for u. U is x plus 2 over 3. So it's 1/3 inverse tangent of x plus 2 over 3, technically plus c. I think that's the right answer. I think I found that integral. Wow. Notice how ridiculously different it looks. Like, don't forget what this problem started as. It started as that. It's like the area under an inverse parabola. Like it's not a parabola, it's parabola upside down. So that's going to create kind of a crazy graph. And somehow the area under that curve is based on inverse tangent. I see, I forgot the inverse. It's based on inverse tangent. I mean, it just seems unbelievable that parabolas are related to arctangent. So it's almost like parabolas and right triangles are related to each other. What? I mean, this is amazing. It's hard to believe. Mind blowing. In order to allow you to be successful in the assignment, you're probably going to have to go back and look at these notes a little bit because I'm going too fast, but we only have like 10 or 15 minutes. And I'd really like to get through some other examples. What about this? This is one that I kind of stole really similarly from your assignment because I kind of have a lot of compassion for the difficulty of these questions. That's terrifying.
This is a different trigonometry one though, isn't it?
Yeah. Now this is very contrived. See that 2x cubed on top? Notice it's cubed. If I switch that to anything else, this wouldn't work. This is very carefully defined. If I made that 2x to the 4th, you're not going to be able to get this right. So which one of these does that look like? Like it's got a shot at looking like one of those. Which one does it look like it could be?
Sine without the cubed?
Yeah, notice you got some that are x squared minus 1, and then you got some that are 1 minus x squared. Notice it's that one. So it's like maybe inverse cosine or inverse sine. Inverse cosine had a negative out front. I don't have a negative out front. So yeah, I think it's actually inverse sine. It looks kind of like that one. Do you agree with that? So the question is, can we get it to look like that so that we can say the answer is inverse sine? Let's try it. Note the integral of, I think I'll write it the other way. I'm going to write it the way your note sheet wrote it. The derivative of inverse sine was 1 over 1 minus x squared square rooted. This looks kind of like that, except for that's not x to the second. So what could I replace that with so it would be jump to the second? Somebody rescue us. I wish x to the 8th were actually, and most people work too hard at this. Like, just what do you wish was sitting there?
Do we just replace that with u to the second?
Yeah, like something squared. You just wish that was something squared. I keep using u, so I'll switch to a different letter this time. In other words, if x to the 8th was some other letter squared, wouldn't that solve the problem? So your gut instinct might be something like, let u to the 4th be x, or you see what I'm saying? Like I find myself thinking like, oh, is it x to the 2nd, x to the 4th? What is it? Well, just write down exactly what you want. It's not that complicated. I wish that x to the 8th was something to the 7th, something to the 2nd. Awesome. Mission accomplished. You now have what you want. But of course, we got more stuff to get rid of, right? And I hope you're algebraically, slowly working your substitutions. I still have stuff to get rid of. I've got a 2x cubed on top, and I've got a dx. And so we're trying to get into W land, but I still have some things that are in the way. So let's keep going. Well, as we have noted, I've got to take the derivative of x to the 8th equals w squared in order to create the dx's and dw's. So the derivative of x to the 8th, would it not be 8x to the 7th times, that's a 7, times dx? And the derivative of w squared would be 2 times w dw.
So couldn't we move the 2x to the 3rd to a separate equation? That way you just have 1 over 1 minus dw, or excuse me, w squared.
You can't pull it out because it's not a constant. You can pull the 2 out, but you can't pull the x cubed out.
Okay.
Now notice that's not very nice. Like I was kind of hoping that 2x to the 3rd would cancel out. Let me show you something a little more creative than that. Like is this helpful? I'm sort of looking at it thinking, gosh, it doesn't look like it's going to be canceling stuff out. It looks sort of disastrous. Would you also agree that if x to the 8th equals w squared, couldn't I square root both sides? It's an equation, couldn't I? So that would mean x to the 4th equals w. In a sense, that's the substitution we could have made up earlier. If x to the 4th is equal to w, then I could replace x to the 8th with w squared. Notice the derivative of this is going to be a lot more fruitful. Because this would imply then that 4x to the cubed dx is equal to dw. That's a switch between dx and dw. You agree with that? Now, were you stuck up top? Like, did I have to do this? No. If I have a w here, isn't w replaceable with x to the 4th? Since w squared is equal to x to the 8th, can I solve that? Can I solve for w and get x to the 4th? And then if you divided x to the 4th over to this side, wouldn't that have got us down to x to the 3rd anyway? Yes. But this one is probably easier. So let's look at what we got now. This is amazing what just happened. I have a 2x cubed on top. I have 1 minus w squared rooted on the bottom. And now I got to switch out this dx, which thanks to this is equal to dw over 4x cubed. What miraculous thing just happened because this problem was canned and very carefully made up. Bam. So those just disappeared. Now I'm home free because I have a 2/4, but that constant can come out front. And now I have exactly what was required to switch out for inverse sine.
So on a test, how are we supposed to find this in the given time? Because I feel like I would spend like an hour just trying to figure this out alone.
I completely agree with you. One, we're going to practice it a lot, but what I said before is true in the sense that I've got to be really careful how to give test questions here, because you're right, Eve. If you, and you know, with a group this size, and because you guys are pretty sharp folks, if you tried the wrong substitution, you'd lose 15, 20 minutes right there. And so this is tough. I mean, I've played with this a lot. I have to be really careful to give you either hints or, you know, not give you near as many problems. Like assume if I give you 5 problems that one of those is going to like burn 40 minutes of your time. And so, you know, maybe the other ones go okay and relatively quickly, but yeah, you're right, Eve. This is stressful to me as a teacher because I do view my role as to teach you math, but it's also to help you get this the heck over with so you can get on with your life, right? It's both of those things. So let's see, that'd be 1/2 then of the inverse sine of W. But W was equal to x to the 4th. So 1/2 inverse sine of x to the 4th plus c. So yeah, it really comes down to, like if I was given this problem on a test, I'd be tempted to put a hint on there and say something like, doesn't this look an awful lot like one of the inverse trig statements? Because we still have a lot of chapters to go. Like I'm going to show you some other techniques. I'm going to show you a new technique called integration by parts. We're going to learn trig substitution. By the time we get to a test, this is going to be one of the things that you know, not all of the things that you know. So I would say that, in my opinion, you know, what's the point of this section? Well, it's to realize it takes a lot of creativity to take integrals. In the real world, most of you are taking this class because some program that you're in wants you to take this class. Can you appreciate that in the real world, you're never going to need to do this? Is it cool? Yeah, it's really cool. I think it is. But in the real world, there's no such thing as an indefinite integral. Does that make sense? There's always numbers there. In the real world, if you were given that question right there, you put it in Desmos and it spits out the answer and you're done, because you're trying to build a bridge. Does that make sense? The only exception to what I just said is if you're making a formula. If you're making a formula, then you know that doesn't go from 7 to 2. You're actually trying to come up with an algebra formula for something. That's the only exception to that. But this is, I want this to seem, you know, kind of cool to you in the sense that, wow, this is, but it's terrifying because it just takes a ton of creativity. You got to come up with the right substitution. Otherwise it doesn't get easier, it gets harder.
You know, Doug, I was looking at the Federal Bureau of Labor and Statistics the other day, and mathematicians, which I think is what you're talking about, creating formulas, had like a 26% like job growth rate, which is higher than I've ever seen any other job.
Recently?
Yeah, this is about maybe a year ago or so, maybe less.
That's really interesting. Yeah, I mean, I think you can see that, you know, part of this is like it's kind of cool to take an integral and so forth, but the other part of this is you're learning to think logically. And that does apply to other things. That's worth something. I don't, you know, does this transfer to not building a bomb that blows up at the wrong time or something? I don't know, but it teaches carefulness, that's for sure. But I just want you to understand in the, you know, as a part of your doing your assignment, like to reach a dead end or reach an integral that you can't take because you didn't make the right choice in a substitution, that'd be normal behavior. Don't feel like you're just supposed to sit there and, you know, try something and it works the first time. Integrals are so different. If you think about it, I'll quit with this. When you take 37 times 19, would you agree there's an algorithm? You just like go. You with me there? Here's what I do. I go 9 times 7 is 63. 9 times 3 is 27. Plus 6 is 33. 1 times 7, 1 times 3. You have this weird little system. Notice I left a space over here. I'll ask you this rhetorically, but I wonder if you could explain to somebody why that weird little system works. And then you add these and you say, hey, look, I found the answer 703. But what if I said, and I'm making this up. Actually, I don't need to make this up. I'll do something better. What if I said divide 23 into 2001? When you multiply, there's kind of a technique to it. But when you divide, isn't there guessing and checking involved in that? Don't you have to kind of try stuff? Like I'm sitting here right now thinking, let's see, 23 goes into 200, I don't know, 7 times. I'm not sure. Is it 7? 23 doesn't go into 20, so 23 goes into 200. So then I find myself going, well, I guess I'll have to check and see. 23 times 7, that's a 2, 14, 15, 16. That's 16, 161. I don't think it's big enough. I think maybe 8. Could be 8, maybe 9. Let's try that. 23 times 8. Isn't this what you do if you don't have a calculator? 184. Yeah, I think that's it. 184. You see how there's like guessing? You got to try stuff. Well, that's no different. We took derivatives and there was a technique and we could just go do it. There's no thinking. It's kind of what Eve said earlier. It's just math. You just go do it. Whereas in this section, we're doing the opposite of derivative, just like the opposite of multiply is divide, and you have to kind of try stuff. This is no different. It's the same exact thing. To take an integral, you got to try stuff, and what you try might not work. I just tried 7, didn't work. Now I got to try something else. It did work. All right, now I can proceed. And do you notice how amazingly good you have to be with your multiplication tables to even guess and check like I just did? If you don't have your multiplication tables memorized, then that problem is going to take you 9 hours to do that long division. And so that's kind of the same thing here. Like, man, I got to try stuff. I'm just learning. I just learned derivatives. I just learned multiplication. So, going backwards is hard. And so again, I'm just saying this to put what you're studying here in context, cut yourself some slack. This is not easy. I did something today, and I need to shut up now, but I did something today where I gave you a bunch of examples that are very similar to your homework assignment. I usually am not purposely prepping you for a homework assignment. I'm just teaching you how to think and then hoping that you can transfer that to your assignment. And that isn't always as nice as a whole bunch of examples. But I think here you need a bunch of examples. This homework assignment is not due until Sunday. I would highly recommend you attack this homework assignment tonight, because I'd love to start class tomorrow with you saying, man, I really got stuck on number 7, because I bet other people did too. And then I can, give you some hints about it. Maybe I didn't get to all the examples is what I'm getting at. And the other thing is this is an example. If you really want to be good at this stuff, you might want to consider looking at the odd problems in your book, the answers to which are in the back of your book, so you don't have to work so hard to check it yourself, and practice this more. That would be good advice in this case. All right, adios. I will post these notes, and as usual, stay after if you would like to talk about your test or anything else.
Hey, Doug, before I go, I just looked it up on Federal Bureau, and from 2019 to 2029, it's 33% growth rate, which when I figured that out, I tried to find another job with that high of a growth rate. Nothing even came close.
I don't know the answer to this for sure, but I'm guessing that has to do with actuarial, because most mathematics has to do with predicting things appropriately. I mean, if you're in a business, it's like, should we buy, should we sell, those kinds of things. If you're in insurance, it's kind of like, is this person, what facts can I collect about Connor to decide if he's going to crash his car? Because he's only paying me $100 a month in insurance. And if he crashes his car, then I'm going to lose money on Connor. So, you know what?
Yeah, it says mathematicians and statisticians. So I think it's kind of covering a really broad range,
Yeah,
but
yeah.
I mean, it's still
And
pretty.
that's what statistics is. You know, one of my favorite stat questions is, you know, you have an airplane that seats 400 people, and statistically, those people do not all show up on the day of the flight. I mean, 400 people, somebody's sick, somebody's mom died, somebody's cat need to go to the veterinarian. Like they had plans, but the day before something came up. And so like 96% of people show up for flights. Well, if you own the company, then shouldn't you overbook it? Shouldn't you book, well, how many should you book? Should you book 408 seats? And if you're lucky, then 400 people show up and you just made 400. I mean, you actually charged 408 people for flights, but you only had to fly 400 of them. You just made 8 times 500. You just made $4,000 extra on that flight just because you knew some statistics.
See, that's something I can get behind if I was a statistician and I booked 408 flights and exactly 400 showed up to fill all the seats, I would get a pretty big rush. That would be pretty cool.
Absolutely. That's nerd high five right there for sure.
Well, the second that one person comes that you overbooked and they're pissed, it's like, oh, God.
Yeah, but remember, you made $8,000. Have you been to a flight? You know what they do? They're like, hey, this flight is overbooked. Would anybody like a $400 voucher? And somebody's like, chang, I'm in for that because I don't have to go right away. They
True.
did 400, but they made 4,000.
And as the statistician, your boss is standing right behind you, has the $400 in his hand, all pissed off.
So, I mean, that's what insurance is doing too. It's the same exact game. How much do I collect from Connor? How do I come up with a number that statistically tells me, you know, when's Connor's first car crash going to happen so that I collect more money than I have to pay Connor? So statisticians are trying to predict the future. They're in the stock market, you know, they're ordering, you know, how many different pairs of what size shoes do you need to order? You don't just order the same number of each pair. You got to look at how many people are size 8, what percent of people are size 8, what percent of people are size 10, etc. And you got to kind of order that percentage. But it's a guessing game because if you end up with a bunch of size 20 shoes left over, there they are on the sale rack, right?
Yeah, it feels a little like gambling.
Yeah, it's totally like gambling. I mean, because that's what it is. I mean, it's the decision-making process. It happens all your life. You know, you meet somebody you like. Man, is this the person? Should I get married to them? Oh man, that's a hard one. You know, I mean, that's all you do is make hard decisions.
Ideally, I don't think that's a hard decision, Doug. That one should be pretty obvious, at least. That's what I think.
It should be.
Well, from a statistic standpoint, what are the odds they take off with all your money, you know?
Exactly, yeah.
You can research as much as you want, but the odds are something off might happen.
See, that's why you marry up, and then even if they take all your money, they have no incentive to.
Damn, it was the correct answer.
But now you just got to convince somebody to marry down.
That's where a sense of humor comes in.
You're exactly right.
I'll see you guys later.
Yeah, have a good one.
See y'all.